Hello everyone, this is our last lecture on AC-DC rectifier. In this lecture, we'll be learning about some basic considerations of while designing rectifiers and basic know-hows. So first, firing angle control. In case of controlled rectifier, firing angle plays a major role. By controlling the firing angle alpha, we can control whether the output voltage is more or less. That is, we get a control of the output voltage by controlling firing angle. The general circuit that is used is for this purpose is an op-amp is used. Here we give a sawtooth wave, and here we give a DC value, and the output we get a pulse. Now, how does it work? Let's see if we draw a graph. The sawtooth wave is from 0 to 1. Suppose 0 to 1 or 0 to any value. So this is our sawtooth wave. Now this DC value is a reference value. Let us suppose this is our reference DC value. Now what happens is, we know what op-amp does. Op-amp compares the two inputs and gives the output. So since we can see that this op-amp does not contain any feedback, that is, it is open loop op-amp. So what open loop op-amp does is, when the input at positive is more than the input at negative terminal, it gives a positive V saturation value or the plus VDD value, and when the input at positive is less than the input at DC terminal, it gives a negative value. Or here, if we count it ground, connect it to ground, it will give 0. So as a result, what happens is if we just mark this here and these things here and there. So what happens is, if this circuit is connected, what happens when the value of the sawtooth wave is more than the DC value? In this case, what it does is, it gives a positive voltage. So it will give a positive voltage, and the level of positive voltage will depend on this VDD. So again, when the value of the sawtooth wave is less than the DC reference, for example in these cases, it will give 0 volts output, because the negative terminal is connected to ground. So we get pulses like this, and these pulses will drive our rectifiers. Now another thing is there, how can we control the firing angle? We can control the firing angle by controlling the DC values. How can we do that? If we increase the DC values to here, suppose, then what happens? This point is here. So we are marking the points. So what happens? For a greater amount of time, the input is 0 and firing angle changes. The firing angle changes from here to here. Again, the firing angle will change, because the pulse goes 1 at a later period. If we decrease the DC value here, let us draw the reference lines. Then what happens? If we decrease the DC values, then the pulse start here. So as a result, what happens is, the starting point of pulse changes, and depending on the starting point of pulse, if this is the alpha, so here the alpha is large, here the alpha is medium, and in this case the alpha is low. So we can see that the value of alpha can be changed by changing the DC value, and this is done in practical applications when we want to control firing angle. Another thing to bring into consideration are linear and non-linear loads. If the current is proportional to voltage in any circuit, then the load is called linear load. Here the voltage is sinusoidal, the current is also sinusoidal. It doesn't necessarily have to be in phase, it can be phase shifted as well, no worries. But input is sinusoidal, output is sinusoidal, then this is called linear load. But what happens when the voltage is sinusoidal but the current is not? In this is called non-linear load. This non-linear load is created because of harmonics presence. So in this case, suppose the frequency of voltage is 50 Hertz, then frequency of the current is also the principal frequency of the current is also 50 Hertz. There is no problem, but the harmonics are present, and because of harmonics, we'll see harmonics at 100 Hertz, at 150 Hertz, 200 Hertz. Because of this harmonics, the wave shape of the current changes, and this type of load is called non-linear load. Non-linear load, in case of our rectifiers, we can see, in case of half wave rectifier, this is our voltage, and our current assumes a form similar to this. So as a result, the current is not sinusoidal, though the voltage is sinusoidal, and our rectifiers generally pose non-linear load, and this non-linear load create a lot of problems. Now, the problems created by non-linear load are mainly issues that has to deal with power factor. So far, what we have learned about power factor. Power factor is the cause of the angle difference between the voltage and the current. That is true, but that is actually called displacement power factor that we have learned in AC circuit. That is one form of a power factor, but this does not explain the power factor in all its entirety. In order to explain the power factor, we have to bring another term into consideration, that is called distortion power factor, which is applicable for non-linear load. So now, how does non-linear load work? Suppose this is our input voltage, and for input voltage we get current suppose we get current like this. So we see this is sinusoidal, our voltage, and our current is non-sinusoidal. As a result, here we have harmonics. The principal frequency still remains the same, that is the frequency of this voltage, principal frequency of this voltage, and this current is same, but there are harmonics. So this current is comprised of one component of current like this, another component of current like this, and there can be other components of currents like this one. So as a result, first, second, third, fourth harmonics are present. That is, the primary frequency is there and multiples of primary frequency are also there. These all create harmonics, and these harmonics create distortion in the output. The output, which is supposed to be sinusoidal, no longer remains sinusoidal, but its shape changes. Not necessarily it will be pulse-like form. It can be something like this as well. What matters is the shape of the current changes from the sinusoidal form. Now, when the when the shape of the current changes, what happens is we have this input voltage, and we have current similar to this in the output. Now, can we measure the angular distance between them? Not necessarily. Not always we can measure the angular distance. In that case, the displacement power factor, it's not the only factor effective. Now we have another power factor which is caused by these distortions available. It is called distortion power factor. The measure of distortion power factor is 1 by root over 1 plus THD whole square. Here THD is the total harmonic distortion. Now, total harmonic distortion is the measure of I square RMS. This is the RMS current of all the components. For example, all the frequency components, which includes primary frequency, its first harmonic, second harmonic, and so on. The sum of all those squared is IRMS square minus IRMS square 1. 1 is only the principal frequency or the first harmonic. So if we subtract the total squared sum of the current at different frequencies from that of the principal frequency and divide it by principal frequency, the measure that we get is total harmonic distortion. Now, what do we want? We want our we want our current to have just one frequency, because the other harmonics are creating our distortion. So again we can see distortion power factor is 1 by 1 plus THD whole square. So we know we want power factor to be 1. Since we want power factor to be 1, we want this THD to be as low as possible. Again, if we consider the equation of THD, IRMS squared, if there is only one single frequency available, IRMS square will be equal to IRMS1 square, because there is only one frequency and there is no harmonics. As a result, total harmonic distortion will be 0, which is our ideal case. So we want IRMS square to be low, or we want the total harmonic distortion in our system to be as low as possible. And the total power factor that we will measure, and that is actually effective, is displacement power factor multiplied by distortion power factor. Displacement power factor is calculated from the first harmonic, from the primary frequency components, and the distortion power factor is calculated from both the primary frequency components and the harmonics. Now, why do we want to improve the power factor or increase the power factor? Power factor is a very important thing. We know that power factor does not affect the real power consumption. That is, power consumption in a load will always be same no matter what the power factor is, because in case of inductive and capacitive circuits or loads, inductive and capacitive loads bring about the power factor. The voltage at the positive end, or the current at the positive side, that is the current which is used to charge the inductor or capacitor, is also consumed in discharging. As a result, the net current becomes 0, or the net power consumed by an inductor or capacitor becomes 0. Then why is the power factor important? Power factor is important because the inductor is connected in a circuit, and in that circuit there are wires which are meant to have 0 resistance, or that are meant to be perfectly conductive. But in real world, the wires are not conductive and there is resistance to it. And this current over here, this positive current over here, when passed through resistance, gives I square R. This I square R, this resistance is our loss factor, and this I square R is completely lost. As a result, we want the current to be as low as possible. We want the current to be only the current that the load is consuming, and not these currents which are caused by the imaginary components. So we want our imaginary components of the current to be 0, or as close to 0 as possible. In order to do so, we make the power factor 1, so that cos theta becomes cos theta becomes cos 90 degree, and cos theta becomes cos 0 degree, and as a result, the current and voltage are in phase. And this will ensure that minimum current flows through the circuit, and only the current that flows through the circuit will be supplied to the load. As a result, this I squared R loss is decreased. So this is why we want our power factor to be low. And when we are considering a rectifier circuit which is converting AC to DC, it is driving a non-linear load, because input is AC and output is DC. So non-linear load, in case of non-linear load, we cannot just consider the displacement power factor. We have to keep the distortion power factor in our mind, and we have to design our circuits accordingly. That's all for AC/DC rectifiers. Thank you so much. In the next lectures, we'll be learning about more different types of power electronic circuits.